This section will discuss how to evaluate a regression. So how well does the line fit? How precisely have we estimated the coefficients? A little bit of hypothesis testing. Um, Fairly straightforward because all of the p-values are estimated for you when you estimate the regression in Excel. So we don't have to do anything except understand what the p-value is and how to determine whether or not a coefficient is statistically different from zero, and look at the r-squared to determine how much of the variation in the dependent variable is explained by the independent variable. So if we go back to some of the examples from our previous slides, so that from the previous section, so this is the example where the dependent variable was food expenditure and the independent variable was income. And we estimated this relationship between income and food expenditure where the intercept was $83.42 and the slope coefficient was 0.1 or 10 cents. And we interpret this intercept as the expected food expenditure when income is zero. So if someone has $0 a month in income, we expect them to spend $83.42 on food. And the inner slope term, the slope term of 0.1, says if we increase income by $1, the average food expenditure increases by about 10 cents. So people are spending about 10 cents per dollar earned on food. And here's the regression output. So we can see the coefficient right here. So that's our estimate of A, the intercept. This is our estimate of the slope. And that's all we really use. So in this section, we're going to think about the r-square, so this number right here. And then we're also going to think about these p-values for the coefficients right here, because this is the result of a specific hypothesis test. And then we have a confidence interval as well. And all of these things can be used together. So when we're evaluating a regression, our objective when we estimate the line is to estimate a line that is as close to the data that we've observed. And we defined close as the line that minimizes the sum of squared errors. So that's the objective that we set when we're using ordinary least squares. So in this line right here, these are observed points. The dots are, the line is the estimated regression line. Each box represents a residual, the difference, or a squared residual. The vertical distance is the difference between what we've observed and what we've predicted. Square it to get a squared residual. Add up the area of all of those squares. That gives you the sum of squared errors or sum of squared residuals. We choose the line to minimize the sum of squared residuals. So we want to choose the line that makes the total sum of all of those boxes as small as they can possibly be. In ordinary least squares, chooses the slope and the intercept to accomplish that. So when we're thinking about evaluating a regression, there's a total amount of variation y. So think about the sample variance. Think back to a previous stats class where you have the sum of what you observe minus the mean squared. That would be your total variation. It's either unexplained or it's either explained or unexplained. So we have a certain amount of variation in food expenditure. So if we go back here to our food expenditure example, there's a certain amount of variation in food expenditure. So if we look at this, food expenditures vary. And as we increase income, food expenditures vary even more. Our goal is to use income to explain that variation. So if income can explain the variation in food expenditures, we're going to see how the r-square and the coefficient and the test statistics and p-values for those coefficients, there will be some information there. So if income can explain food expenditure, or if it is a variable that explains food expenditure, we'll expect to see something called an r-square that will not be equal to 0. And then we'll see coefficients that are statistically different from 0. But notice how food expenditure varies. There's variation in food expenditure, and we're trying to explain that with income. So the total variation is very similar to the sample variance. The portion of that, the explained variation is a portion that is predicted. This isn't technically correct. predicting and explaining are two different things, but just for right now, think about it as the portion that we predict. And then there's the unexplained, which is the portion that we did not explain. I mean, it's fairly self-explanatory there. The R-square is a number. It's a sample statistic, just like an average or something else, that tells us how much of the variation in the dependent variable was explained by the independent variables. So it's just a ratio. So this R-square is always going to be between 0 and 1. So we have the amount of the variation we explained divided by the total variation. That number is going to give us the R-square. Ignore the squared part for right now. It's not really that important. We're not going to think about the R, just the R-square. So it's the explained variation divided by the total variation. And let's look at a couple of examples that will help you visualize what the R-square is actually doing. So in this first plot right here, again, this is made up data, so ignore the actual values here. This line right here, just under 202, is the average value for food expenditure in this example. So the total variation in food expenditure, we're thinking about the sample variance in food expenditure, you would take the dot minus the mean, square it for all of those, add them up, and divide that by n minus 1. That would give you the sample variance for food expenditure. So think about the total sum of squares as being, or the total variation y as being the dot minus the mean squared for each one of these points. Notice all of the points fall directly on the line. So the line that we have estimated goes precisely through every single point. So the total variation is exactly the same as the explained variation in this example. So we get an R-square of 1 because the line that we have estimated has perfectly predicted every single point that we observe. In this next example, where the R-square is really low, 0.025, notice if we take the dot minus the mean, this right here, this distance would be the total variation. Think about the total variation for that point, or how much it varies from the mean. And most of that is unexplained. Because remember, the difference between what we observe and what we predict is the residual. So if we look at the residual, the dot minus the line, that makes up the majority of what we observe on the dot minus the mean. So in this case, most of the variation is unexplained. And notice how close the line that we estimated is to the actual mean. So the slope is very, very flat, and it's very close to the actual mean. So if you have an R-square of 0, what that technically means is the independent variable explained 0 of the variation in food expenditure. So if you were going to if your goal was to explain food expenditure, you might as well just use the average value of food expenditure as your best guess. Having knowledge of the person's income does not help you predict food expenditure. If that's the case, your R-square is going to be 0. It's rare to get an R-square of exactly 0 just because some randomness you might explain some of the variation. But in an example like this, the R-square is going to be quite low. Now this bottom left, the R-square is 0.86. And notice the points are close to the line, but not exactly on the line. So they're further than we get in this plot, but closer than we get in this plot, and we get an R-square of 0.86. So this ratio would tell us that the estimated regression equation explained, or the independent variables explained 2.5% of the variation in food expenditure. In this example, income explains 86% of the variation in food expenditure. In this top left example, income explains 100% of food expenditure. So the closer the points are to the line that you estimated, the higher your R-square is going to be. So if the R-square is 0, your y-hat is basically y-bar. You might as well use the average value of the dependent variable for your prediction, because knowing the value of income doesn't provide any useful information. So when we're thinking about the R-square, it's just a ratio of how much is explained divided by how much could possibly be explained. And the closer that ratio is to 1, the better our predictions are going to be. A 1 is perfect prediction. 0, we explain nothing. Our regression equation did no better than the sample mean. We typically see an R-square somewhere between 0 and 1. What you have to be careful about, we'll talk about this in a little bit, in just a few minutes, your objective isn't necessarily to get the highest R-square. There are cases where if your R-square is low, close to 0, that may indicate a problem, but that's not always the case. It's possible to have a really high R-square and still have a problem with your regression. And it's possible to have a low R-square and your regression is actually perfectly fine. There's nothing wrong with it. It's just a gauge. It's something we use to look at, but it's not the end-all be-all measure of how good your regression actually was. So in the Excel output, this is where we see the R-square. It's this number right here. So this is the data that we used in the previous example. So if we're looking at this plot right here, so this is the actual data and the estimated regression line right here. Notice the line does approximate that relationship. It's not perfect, but it's better than nothing. And this tells us that the variable income explains about 39% of the variation in food expenditure. So if 39% of the variation in food expenditure is explained, the remaining variation is unexplained. So 61% of the variation in food expenditure would be explained by something other than income. So how old the household members are, how many household members there are, where the household is located, the employment status of the household, do they have any dietary restrictions? All of those are variables that would explain food expenditure, but they're not in the model. So the variable income is the only thing we have included in the model. That explains 39% of the variation. That other 61% would be explained by other factors. And it's impossible to determine all the factors that explain food expenditure because there's going to be some randomness household to household that we're just not ever going to be able to capture in regression or with a regression. In multiple regression, it's the same idea. We have an R-square here, so about 87% of the variation. So we would say the included independent variables, so in this case, square footage, age, pool, fireplace, and college, explain 87% of the variation in the sales price of a house. Then we're never going to have a model explain 100% of the variation in the sales price of a house. In this case, we have 13% of the variation left unexplained. And that could be due to a number of factors. The size of the lot that the house is on. Is it a brick house? Does it have vinyl siding? Does it have a metal roof? Does it have a composite roof? Does it have energy efficient windows or non-energy efficient windows? Those are all variables that would help explain the sales price and might help us explain that remaining 13% of the variation. But we would never expect to explain all of it. Bedrooms, bathrooms, square footage, location, that's going to explain most of it. And these other factors help explain variation as well. So this is the number you're looking for. Just multiply that by 100. So we would say 86, we'll just round that up, 87% of the variation is explained. Don't worry about the multiple R, adjusted R square. These are more for this is more for a diagnostic thing that we'll think about later. A couple things to remember about the R square. Adding an additional variable will never cause the R square to go down. If you add another variable to the regression, so let's say in this right here we add another variable for the size of the lot, the R square cannot fall below this 87%. Adding more information cannot harm the R square. It cannot cause it to go down. It may not cause it to go up, but it cannot cause it to go down. Because the worst that new variable does is explain no additional variation. The best possible scenario is it explains the rest of the variation, but that's unlikely. So your goal should never be to maximize the R square. If your objective is to maximize the R square, you can end up in a situation where you add variables to a regression that don't belong in the regression. So these are variables that you probably shouldn't put in the model, but you're desperate trying to raise that R square, so you include them anyway. And that can actually create some problems that we'll talk about a little later. A low R square does not mean your model is bad or wrong, and a high R square does not necessarily mean your model is correct. There are several cases where if you get an R square that's really close to 1, it's an indication that you've probably done something incorrect. Some relationships, so if you're thinking about some time series data and you're looking at a stock price, not the returns, but a stock price over time, it's very, very easy to get an R square that's close to 1. But that doesn't mean your model is correct. There are some dependent variables that are hard to explain. So if you think about the birth weight of a child, there are a lot of factors that explain how much a child would weigh, and it's just hard to predict. I know you can have ultrasounds and checkups with the doctor prior to the delivery, and they could still be off by 20-30%. I know with our second child, they were anticipating almost 10 pounds, and he was born at the high 7s. So there's a lot of just, it's hard to explain. So the health of the mother, the diet of the mother, the race of the mother, the age of the mother, all of these things explain some of the variation in birth weight, but it's most of the variation is going to be unexplained. The sales price of a house is pretty easy to explain. Observable characteristics do a really good job explaining the variation in the price of a home. Birth weight is hard to explain. Even if you have all the observable characteristics, it's still hard to explain. How long it takes a house to sell is a hard variable to explain. The R squares tend to be quite low for sales price, not for sales price, for days on market regressions. So if you want to use observable house characteristics to predict the price of a house, you can do a pretty good job. If you try to use the observable characteristics to explain how long it takes that house to sell, it does not do a very good job. All right, so now we can think about hypothesis testing. And this is actually fairly straightforward because all the tests are already done for you. All you have to do is look at the p-values and know how to interpret a p-value. So going back to the food expenditure example, this is the estimated regression equation. So this is the intercept, this is the slope. What we really want to think about with hypothesis testing in regression is the slope coefficient statistically different from 0. So in this case, 0.1 is the slope. So we would say on average, if we increase income by $1, food expenditures increase by 10 cents. But is it statistically different from 0? So 0.1 is not equal to 0, but is it sufficiently different from 0 to say we can reject the null hypothesis that in the population, income has no impact on food expenditure? So that's what we're thinking about with hypothesis testing. So the null hypothesis is that the coefficient equals 0. And if the coefficient equals 0, so if in the population, so let's go back to, this is fine here. So if we go back to regression like this, so if the null hypothesis is that B equals 0, then that means the true model is just A. So if B equals 0, that means this term goes away and the variable X does not have any impact on Y. So the null hypothesis is that the independent variable has no impact on the dependent variable, holding the other variables constant in the general case with multiple regression. The null hypothesis is the coefficient is not equal to 0. So in this case, 0.1 is not equal to 0, but if you remember from our previous section on hypothesis testing, we have to think about, is it sufficiently different from 0 for us to reject the null hypothesis? So it depends on a lot of things. How much of the variation is unexplained. So if our residuals are large, if our sample sizes are small, those are all things that can lead us to a fail to reject. So there's only one hypothesis we're going to test. Is the coefficient statistically is the coefficient equal to 0, against the alternative that it's not equal to 0. And all you have to do is look at the p-value for the column for that in the row, look in the p-value column for the variables that you're looking at. If the p-value is less than alpha, we reject. So if you're using 95% confidence, you want a p-value less than 0.05. If you're using 99% confidence, you want a p-value less than 0.01. If you're using 90% confidence, we want a p-value less than 0.1. And we're never going to think, we won't think about p-values, any confidence level less than 90%. You can also look at the 95% confidence interval, and that would allow us to test any hypothesis that we want, not just 0. But the p-value that it spits out is specifically for the null hypothesis that the coefficient is equal to 0. In multiple regression, we just have a separate hypothesis test for every question. So we would test, is this coefficient different from 0? Is this coefficient different from 0? Is this coefficient different from 0? So there's a different hypothesis test for every coefficient, which is why you see a p-value for every single coefficient. What we have to think about in the multiple regression setting is holding the other variables constant is the relationship between the independent and dependent variables statistically significant. We're in a simple regression with like this, we don't have any other variables in the regression, so we're just thinking about that coefficient. In the multiple regression, we have to think about holding these variables constant is that coefficient statistically different from 0. So you can always just same null and alternative. So in this case, this is the same output that we had earlier with the food expenditure. So the coefficient is 0.1. The p-value, this says move the decimal place to the left 5 places. And we can see that p-value is certainly less than 0.05. So we would reject the null hypothesis that it's equal to 0 and conclude that income is a statistically significant determinant of food expenditure. So in this case, we reject the null hypothesis that the true effect of income is equal to 0. If you look at the 95% confidence interval, notice that 0 is not in the interval. So our 95% confidence interval for the true slope coefficient for income is somewhere between about 6 cents and 14 cents, and 0 does not fall in the interval. So all of these things are consistent with our previous hypothesis test, where p less than alpha, reject the null hypothesis. The null is equal to 0, so we reject equal to 0 in favor of the alternative. So in a multiple regression setting, we would look at all these different p-values. We don't care about the intercept p-value, but we can see for all of these except fireplace that they are statistically significant determinants of the sales price of a house. So holding constant the other variables, square footage is a statistically significant determinant of the price. Age is a statistically significant determinant. Whether or not the house has a pool is a statistically significant determinant, but fireplace is not. Notice the p-value there is 0.15. So this coefficient tells us that on average, homes with a fireplace sell for $1,398.80 more than homes without a fireplace, but that's not sufficiently different from 0 for us to reject the null hypothesis. And if you look at the 95% confidence interval, 0 falls in the interval. So with 95% confidence, we believe the true effect of having a fireplace on sales price is somewhere between negative 518 to positive 3,315. So 0 is in the interval. So we cannot reject the null hypothesis with 95% confidence for fireplace. So whether the home has a fireplace or doesn't, the house may or may not sell for a higher amount. Then college has a p-value of 0, which is highly, highly significant. These t-stats, we don't really look at these in regression for hypothesis testing because the critical t-value, if you recall from our previous hypothesis testing section, depends on the sample size. So we choose our level of confidence, but we also need the number of degrees of freedom, and that depends on the number of independent variables in your sample size. So your t-stats, they vary problem to problem. but the p-values do not. So if you look at your p-value column, p less than alpha, reject the null hypothesis. And just remember, the null hypothesis is no effect. And if your p is less than alpha, that means we're saying we're rejecting the null in favor of the alternative of not equal to 0. So very simple test. If the p is less than alpha, that independent variable is a statistically significant determinant of the dependent variable, holding the other variables constant. We also need to think about outliers. Outliers can affect our inference because they can change this, have a significant impact on the slope of the lines that we actually estimate. So this is the original data and the original regression, and our tables told us that we reject the null hypothesis that income, the coefficient on income equals 0. So we're 95% confident that income is a statistically significant determinant of the food expenditure. Notice what happens if I change one observation. So I take this observation right here, this lowest observation, and I pull it way up here to like 900 or something. I make it really, really big. Notice the line that we estimate is now $239.86 for the intercept and 3 cents for the slope coefficient. So the coefficient's about 1/3 the size as it was before. That one observation really affected the slope and intercept. So when we're doing our hypothesis testing, if it changed the slope, it's going to change the test statistic. If it changes the test statistic, it's going to change the p-value. If it changes the p-value, it could affect the outcome of that hypothesis test. So notice what happens when we took that one observation and we created an outlier. Our p-value on income increased to 0.35. So now we are no longer finding a statistically significant relationship between income and food expenditure, and the only thing that changed was the value of one observation. So when you have outliers, you have to look at your data before you start estimating your regression to make sure something like this isn't going to have a significant impact on your results. Outliers are a really, really big problem when you have small samples. So in this case, our sample size was 40, so that one observation was getting a lot of weight. If we had 40,000 observations, that one outlier probably wouldn't have affected anything. It might have changed it a small amount, but it wouldn't have had such a significant effect on the overall results. So pay attention to outliers and pay close attention to outliers when your sample size is small, because that's when they're going to get the most weight. We went from finding a statistically significant relationship between income and food expenditure to no statistically significant relationship. And the only thing that changed was one observation. Now, if that outlier had been somewhere in the middle, right here, it may have just pulled the line up. If it was over here on the tail end, it might have made the line even steeper. But either way, it's going to affect the results of the hypothesis test when your sample sizes are really small. So I mentioned earlier that your goal should never be to maximize the R-square, because you can add what we call irrelevant variables. So a variable is irrelevant if it has no relationship with a dependent variable. So if you add a variable to a regression that has absolutely no relationship with the dependent variable, you can create problems for your other variables. So when you start adding things to the regression that don't have any relationship with the dependent variable, the standard errors for the other coefficients become larger. So the standard errors are what you see in this column right here, which is very similar to if you're thinking about x bar and the sampling distribution of x bar. We had sigma over square root of n. That was the standard deviation of the sampling distribution of x bar. That's similar to what we're thinking about with the standard error. It's the standard, it's basically the standard deviation of the sampling distribution of our coefficients. it tells us how precisely we've estimated the coefficient. So the smaller the standard error, the more precisely we have estimated the coefficient. And when you add variables to a regression that do not belong, the standard errors for all of the variables can become larger. So you can actually lose precision on the other coefficients as well. So it could be that there is a statistically significant relationship, but you're not detecting it because you've added a variable that is irrelevant. So you have to think carefully when you choose the variables for your regression. You need to have a good reason for putting it in the regression. If you can't think of any reason theoretically or using any other basis for why that variable should be included, think twice before you put it in the regression. So maximizing the R-squared can create some problems if you care about the hypothesis test for the particular coefficients. If your only objective is to make a prediction, it's not as big of a deal. But if your goal is to detect significant relationships between specific variables in the dependent variable, it can definitely create a problem. So that's including a variable that's irrelevant. Excluding a variable that is relevant is a major problem, and that's what we call omitted variable bias. So you can actually cause the coefficients on the other variables to change if you omit a variable that belongs in the regression. So if you have an important variable that's correlated with the dependent variable and the other independent variables as well, omitting it can create some pretty serious problems. And this is what we call omitted variable bias. So as a quick example of omitted variable bias, this is the regression that we estimated using all of the data for the sales price regression. So this just replicates the coefficients from the table that we estimated previously, or from the regression that we estimated previously. And the coefficient on, let's just look across these. So this is the model with all the variables. This regression omitted square footage. So I did not include square footage in this regression. The intercept changes, but we don't care about the intercept most of the time. Square footage is omitted. Age is negative 192 when we include square footage and negative 269 when we omit square footage. So notice dropping one variable caused the coefficients on the other variables to change. Notice it's still statistically significant. Our p-values are still less than 0.05, but we definitely changed the coefficient. On pool, we estimated a coefficient of 4,352 when square footage was included, 4,380 when square footage is excluded, and we went from highly significant, p less than, this would be significant at the 99% level, to now we're not quite significant at the 95% level. So the coefficient didn't change that much, but our p-value did change on square footage. But look at fireplace. This is the biggest difference. When we include square footage in the regression, the effect of a fireplace is about $1,400, and it's not statistically significant. So there's no statistically significant relationship between fireplace and the price of a house when we included square footage. When we omit square footage, the coefficient on fireplace is now 6,237 and highly significant. And what that tells us is there's likely a relationship between fireplace and the size of the house. That if homes with a fireplace tend to be larger than homes without the fireplace, when we omit square footage, this fireplace variable is now proxying for the size of the house as well. So we're now capturing the effect of a fireplace and the effect of house size. So the omitted variable bias comes through the correlation between the omitted variable and the other variables and the dependent variable. So if homes with and without pools tend to be about the same size, we wouldn't expect the coefficient on pool to change very much. And that's probably what's going on right here. There are some smaller homes with a pool, some larger homes with a pool, but there's no real strong correlation between house size and whether or not the home has a pool. but there could be a pretty strong relationship between the size of the house and the presence of a fireplace, where larger homes are more likely to have a fireplace than smaller homes, and the coefficient reflects that. If you look at the college town dummy, didn't change a lot. So homes in college towns tend to be about the same size as homes not in a college town. So the coefficient didn't change. But that's omitted variable bias. The coefficients on the other variables changed when you omitted one of the other variables. And the R square fell as well. So R square went from 87% of the variation being explained to 54% of the variation being explained. So if you add a variable and your other coefficients change dramatically, or you omit a variable and your other coefficients change dramatically, you need to do a little more digging into what the appropriate regression actually is, and do you believe that variable belongs, or do you have a sound theoretical reason for why that variable should be omitted? So that's inference. The big takeaway here is P less than alpha, reject the null hypothesis for hypothesis testing. If you see small p-values, that means the relationship between the variable and the dependent, that variable and the dependent variable is statistically significant. And then on your R square, the higher it is, or the closer to 1, the more of the variation you explained. The closer to 0, the smaller amount of the variation you explained. But your objective should never be to maximize it. You need to be cautious and be intentional about the variables you include in the regression, because just adding things in just to try to get a higher R square can actually create some other problems. So in the next video, I will have some Excel examples where I show you how to estimate the regressions, some things to look out for, and then you can start estimating your own regressions and then interpreting the output and